This lecture video will cover collision theory. Please read the OER textbook chapter section 12.3 for more details. From the previous lecture video, you see factors that affect reaction rate. We're looking at the physical state of reactant. We're looking at the concentration of the reactant. We're looking at the temperature and also catalyst as well. And as you observe, when the surface area of the reactant increase, the reaction rate go faster, right? It's going to increase as well. And when you're looking at the concentration of the reactant as well, as you increase the concentration of the reactant, the reaction rate also increases. And you observe that as the temperature increases, the reaction rate increases. And the last one, you observe that the catalyst speed up the reaction. Okay, so in this video, we are going to use collision theory to explain these phenomena. Okay, so the collision theory states that for a reaction to occur, the molecules must collide to react with one another and also with sufficient energy and also with correct or proper orientation. So these three themes is going to help us to explain the phenomena that we observe above. Okay, so let's take a look at each. Okay, so I'm going to plot the graph. Okay, so I'm going to plot the graph, which is called reaction coordinate diagram, which is going to plot between the reaction progress or as the time progresses by what happened to the reaction against the energy. Okay, so we're going to measure this in joule per mole. Okay, so because when you have a reaction, you are going to need to start with reactant, right? So that means you are going to start with reactant, and as the time progresses, that reactant is going to become product, right? So we have two substances right now. Okay, so we have reactant and we have product. And as you see, right, as the time progresses, right, reactant will eventually become product. Okay, so according to the collision theory, for a reaction to occur, molecules must collide, right? So that means in this case, molecules of reactants must collide with one another. So as it collide, it also need to collide with proper orientation as well. Okay, so when they arrange themselves, they collide with proper orientation, they are going to achieve the point what we call transition state. Okay, transition state is a state where the bond is breaking and forming. For example, if you have two molecules, right? So for example, A and B together, they are going to need to collide, right? So as it collide, molecule A is going to break bonds, right? So the bond within molecule A is going to be break. Same thing for molecule B as well. And then atom from the molecule A will start to form a new bond with the atom from molecule B. Okay, so that state right there, when the bond is breaking and forming, this state right here is what we call transition state. So the transition state is going to be the state where the two reactants need to collide with each other with the proper orientation, which means that if it collide without proper orientation, is going to lead to the unproductive pathway that lead to something else that is not product. Okay, so now the second thing that we're looking at the collision theory is that it's not only have to collide with proper orientation, but it's also need to collide with sufficient energy as well. Okay, so the sufficient energy is going to be what we refer as activation or the activation barrier. Okay, so this energy is the minimum amount that required to initiate the reaction. For the reaction to occur, the molecules of the reactant need to overcome this mountain, right? Overcome this activation energy in order to convert to product. This activation energy from the reactant to product, this one right here, we refer as the forward direction, right? Because you are going forward direction, going from reactant to product, right? So this is the activation energy of the forward direction. Okay, so if you're looking at the reverse process, right? So the reverse process would happen when the product actually convert to the reactant. So if you're looking at that way, you also can calculate for the activation energy for the reverse process as well. Okay, so the reverse process would imply that it's going from product to reactant. So in this case, the difference between the energy of the product and the reactant, this is what we refer as enthalpy change. Okay, so in this case, as you see the enthalpy change, in this case, as the product is higher energy than the reactant, therefore the delta H is going to come out to be a positive value. So this is going to refer as endothermic process. Okay, so endothermic process is referring at when you have the energy of the product higher than the energy of the reactant. Okay, so if you're looking at in terms of the rate, right, or the speed of reaction, you can see that the activation energy that required for the forward process is a lot higher than the reverse process. So in this case, in order to overcome this mountain, right, so it's going to require a lot of energy, making the rate of reaction to actually go very slow. So in this case, you see that the relationship between activation energy and the rate is going to be inversely proportional to each other. Okay, so if the reaction has high activation energy, the rate of reaction would be slow, right? Because the molecule require much more energy to overcome the activation barrier, right, in order to convert to product. Okay, so for now, I want you to know that this K is the rate constant. We're going to talk about this in more detail when we talk about in the next lecture video. Okay, so this is the rate constant. Okay, so note that the rate constant is directly proportional to the rate. Okay, so that means in this case, as the rate is being slow, the rate constant is also going to be a low value as well. Okay, so all right, so if you're looking at the reverse process now, right? So if you're looking at the reverse process, you can see that the activation barrier for the reverse process is actually much lower than the forward direction. So that means in this case, as the activation energy low, the rate is actually going to go faster, right? So in same as for the rate constant as well, it's going to be in a faster rate. So in this case, you can see that the reverse process is actually going to happen in a faster rate than the forward process in this case. In summary, this is the graphical representation of the collision theory. Okay, so pretty much we know that for the reaction to occur, right, molecules of reactant must collide with proper orientation. So the transition state is actually described that it have to be collide with proper orientation and also with sufficient energy as well. And this activation energy is explained the sufficient energy term of the collision theory. Now let's take a look at example. Okay, so in this case, we are going to label reactant, product, and transition state. Okay, so that means this case, right? So according to the reaction progress, okay, so reactant would be the first step right there, and reactant must collide with proper orientation, right, to achieve the transition state, right? And then it's going to result in product at the end. Okay, so if you want to know the activation energy, you are going to need to calculate from the top of mountain to the energy difference between the top of mountain, which is the transition state, and the reactant. Okay, so in this case, it's going to be that, right? So this is, we are looking at the forward direction. Okay, so so that means it's going to come out to be 5 kilojoule per mole. Okay, so now what is the size of the enthalpy change? When we are looking at the enthalpy change, we are looking at the energy difference between product and reactant. Okay, so in this case, the change in energy between product and reactant, remember the change, the delta is always have to be final minus initial. The final in this case, product has lower energy than the reactant. Therefore, the size of the delta H would come out to be a negative value. Okay, so in this case, it's going to be 5 minus 15, it's going to be negative 10. The negative sign indicates that this reaction is exothermic process. Okay, so for exothermic process, the energy of product is actually lower than the reactant. Okay, now if you're looking at the activation energy for the reverse process, which means in this case, you are going to compare between going in the reverse direction, right, from the product to the reactant. So for the activation energy, it's going to be the top of mountain and the product, right? So the difference between that two. Okay, so that means in this case, the reverse activation energy would be 20 minus 5, so it's 15 kilojoule per mole. Note that the activation energy is always going to be a positive value because the amount of energy that's required, right, to achieve the transition state. Okay, so in this case, you can see that if I ask you which one would be faster, the forward direction or the reverse direction, right? So you can see here, the forward direction would be faster than the reverse direction because forward direction requires less energy than the reverse direction. The next example that we are going to take a look at is we are going to take a look at the proper orientation of collision. Okay, so in this case, what I have is the alka-sulfur reaction. Okay, so we have the bicarbonate react with the acid from citric acid. Okay, so it's going to yield water and carbon dioxide. Okay, so in this case, what we are going to take a look at is I'm going to give you several options of how the molecule can collide. Okay, so this structure right here is going to represent the bicarbonate. Okay, so we are going to collide the bicarbonate with the acid. Okay, so these are the different orientation. Okay, so we have 5 different orientation where hydrogen can collide. Okay, so the first one is hydrogen can collide with the bicarbonate, like with this hydrogen of the bicarbonate. Okay, so the second one you see is collide with this oxygen right here. Right, the third one is between these two. Right, the fourth one is between these two, and the last one is between these two. Okay, so we're going to take a look at which one is going to lead to the productive collision. Okay, so which means it's going to lead to the result. Our result would be the product, right? So remember, our result need to be water and carbon dioxide. So that means any collision that doesn't look like it's going to form water and carbon dioxide, those are going to be the unproductive collision. Okay, so in this case, if you're looking at this, right? So if you collide these two, it's not going to make water because water is H2O, right? So it's going to form that, right? So the two hydrogen need to connect with the oxygen. So in this case, if you collide these two, it's going to form bond between hydrogen and hydrogen, right? So that's not going to be our water, right? So that means the orientation one is not going to be productive pathway. Now let's take a look at orientation two. Okay, so orientation two, as these two collide, what you are going to observe is that eventually it's going to make that, right? Hey, that's kind of look like water, right? So that means in this case, what you are going to observe is that eventually this bond between oxygen and carbon probably going to break, right? So this bond is going to break, and eventually you are going to see that, yep, that's molecule of water, and yep, that's molecule of carbon dioxide. So that means in this case, orientation two would be the productive collision or the proper orientation, okay, so that lead to the product. Okay, so why 3, 4, and 5 is not going to be productive collision? Well, it's just because that if you collide any of this, right, it's not going to form carbon dioxide and water. Okay, so that's why the rest of those are unproductive pathway. Now I'm going to bring this and represent this into the graphical representation as we see earlier using reaction coordinate diagram. Okay, so we are going to plot graph. So on the exam, you are going to be expect to either plot graph like this or read graph and then extract the information similar to the example one that we see previously. Okay, so it's going to be one of those two. Now let's take a look at B. Okay, so how can we draw this? Okay, so again, the reaction coordinate diagram is going to plot between energy and the time, right, or reaction progress, right? So in this case, it's going to be that. Okay, so it's going to start with, again, reactant. So reactant that we are looking at going to be these two. It's going to be that two. Okay, so it's going to be these two together. They're not collide yet. Okay, so they're going to be separate. Now they need to collide, right? So they need to collide with sufficient energy. So that means they need to go up to a certain amount of the activation barrier, right? So they need to go all the way to achieve that activation barrier, and they are going to have to collide with proper orientation. The transition state right here is what we refer as orientation 2. Okay, so this transition state or the proper orientation that we are looking at is this one right here. Okay, so it's the orientation 2. Okay, so pretty much it's going to indicate that this bond right here between oxygen and carbon is going to be break apart, and this bond right here between oxygen and the incoming hydrogen is going to be formed. Okay, so this is where the bond is being formed and also being broken. Okay, so the next thing, as the bond is being formed and also being broken as well, after the transition state, then it's going to become the product. Okay, so how do I know the product has lower energy than the reactant? Well, the reaction give off heat. So therefore, in this case, I know that the amount of the energy for the product would be lower, right? Because eventually, if you calculate for the change of enthalpy, it need to come out to be a negative value to indicate this is the exothermic process. The next thing we are going to take a look at is we are going to use the collision theory to explain this effect that we see in the previous video. Let's take a look at the first factor, which is the surface area. Okay, so in this case, as the surface area increases, right, so which means that if the reactant are broken into small pieces, right, that allow for a larger surface area of interaction, the chance for more molecules of reactant to collide with one another is going to increase, and this is going to result in the number of collision increase, and it's going to lead to the rate of the reaction increases as well. Now, if you're looking at the effect of concentration, we are going to see that as concentration of reactant increases, molecules of reactants collide with more frequently. And as the frequency of collision increases, the rate increases as well. So now if you're looking at the effect of temperature, you will see that as temperature of reaction increases, molecules will move faster. And as molecule move faster, molecule will collide more frequently with greater energy at higher temperature, right? Increasing the likelihood that the reactant will be able to achieve the activation energy. And the last one, the effect of catalyst. Okay, so catalyst will accelerate the reaction by lowering the activation energy by providing the alternative pathway. What do I mean by that? Okay, so let's take a look at this. Okay, so this graph right here is going to represent the uncatalyzed pathway. Okay, so uncatalyzed pathway has a very, very high activation energy. Okay, but when you introduce the catalyst will provide an alternative pathway. For example, the uncatalyzed might be one-step pathway, but the catalyzed reaction might be two-step or multi-step pathway. but this pathway would yield a lower activation energy. Okay, but eventually it needs to lead to the same product. Okay, so that's what it means. So note that the only thing that lower the activation energy is the catalyst. Everything else, the activation energy will stay the same. The collision theory can also be represented by the mathematical equation called Arrhenius equation as well. So this is the Arrhenius equation. K is the rate constant. Okay, so this is going to, we are going to look into more detail when we talk about the reaction. Or just note that the rate constant is directly proportional to the rate of the reaction. Okay, so if you see the high value of the rate constant, it indicates that the reaction speed is going to be fast. Okay, so A is going to be what we call frequency factor. Frequency factor is going to represent two things from the collision theory. One is the collision frequency, which is molecule have to collide, right? And the other one is the orientation frequency, which is it need to collide with proper orientation. Okay. And the last factor is called exponential factor. Exponential factor would have two terms. It's going to have the activation barrier term and also it's going to have the temperature term as well. Okay, so what all this mean? Okay, so the Arrhenius equation is going to explain the same thing that we see previously, which is going to be as the activation energy increase, right, the rate of reaction would decrease because the rate constant. How do I know that, right, from this Arrhenius equation? Well, I'm going to take a look at this, right? So the EA value right here is part of the exponential factor, which if you're looking at is the negative exponential. Okay, so that means in this case, the negative exponential is going to have the inverse relationship with the K value. Okay, so as you see here, right, so as the EA increase, right, the K value would decrease, and that is going to affect the rate, right? The rate would be slower. Okay, so now if you're looking at the temperature in this case, temperature is part of the exponent, but is part of the inverse of the exponent. So that means the temperature is going to have the direct relationship with the K, right? So in this case, as the temperature increase, the K value is going to increase, and that is going to result in a faster rate. Okay, so for the exam, you don't actually need to know how to calculate for this. We are going to take a look at this just in terms of relationship. So here is the summary of this video, right? So we're looking at the collision theory, which state that for a reaction to occur, these things need to happen, right? So one is molecule must collide to react with one another, and also they need to collide with sufficient energy and also with proper orientation as well.